Thank you, Raj, very much. I have been associated with Brillio for, as Raj mentioned, for a couple of years. And it has been a great experience, and I've been very impressed with the Brillio team. And what I'm going to do today, I claim that my talks are fractal, self-similar. If I stop at slide number 1, and that's it, then I should have been able to communicate my message by then. If I stop in the middle, if I am lucky enough, go through the end, then that's very good. But you shouldn't have to wait for the end, okay? So what's my message, okay? So first thing is, a lot of this excitement that you hear, that's real. Things are different than they used to be 10 years ago, and that has to do much more with computing power and access to data than with anything else that has happened new. Most of the techniques that are being used have been around, like machine learning techniques, the idea of deep learning, they have been around for 20 years, maybe 30 years in certain cases. But what was not around was access to large-scale computing and availability of large-scale data. So as I was mentioning, since there is a large Indian heritage population here, where the word data comes from? It comes from data. It's exactly the same root as in Latin, is to give, to offer. So that's what data means. So it's whatever the sensors offer, and wherever you get it from, the people who are generating the data offer you that, and it gets directly tied to privacy issues, which we're going to come later. Since the data is not yours, then you have to treat it with respect. Someone is giving it to you. So anyway, so data, again, the very concept of data, as you can now tell, is since the inception of humanity, right? So first point is that this revolution is real. Second point is that even though advances have been made, we are truly scratching the surfaces. So you hear a lot about the deep mind. You hear a lot about Cortana or Alexa, these big people who get the center stage, and they get articles in Wall Street or Forbes or New York Times almost every other day. Don't be intimidated. They do not have the understanding. We as a human race do not have the understanding to solve the AI problem the way we perceive it. What's happening is mostly at the skin level. And that's where I think great organization and a business place like Brillio and the customers you have, you can work together to solve your problem without being intimidated, without being overshadowed by the Googles and Facebooks. My students go and work for them. They get paid very highly, bigly, as Trump would say. Right? Starting 27-year-old, my Chinese graduate student who doesn't speak English very well, brilliant, codes well, he got a startup package of $300,000 at Google, 27-year-old. The guy with all his brilliance does not know much. Please. Right? But I'm happy for him. It's great that they're gathering all this. You guys collectively know a lot more than I do. Okay, so this, whatever I'm going to talk, I want to be the medium, not the speaker. Okay, so stop me anytime. Being rude to me I take it as a compliment. Okay, so that's the message. Third thing is that there are things we can do, that will take the frontier further. And we really need to invest as a society in that, and that usually doesn't happen. So what happens with all these fields is you see a spurt, and then it goes through a long period of fallow because, society doesn't want to invest in very things that it does not know. The moment it knows, that means it's already known, right? So it's a process. So my message would be the following. Stop me anytime. You know collectively more than I do. So if you have questions, which probably are real, James and I, here's James, had a great conversation yesterday during dinner, and I think we connected, right? So that's my goal, okay? So coming to first, yes, you have heard all of this, There's a great amount of resources being put, and most of it is, some of it is real, the computing power, the data, and they have, what they're doing is they have a huge population customer base, huge number of eyeballs. So if they can push the envelope epsilon, they get 1 million times epsilon in return, right? And so they're putting in a lot of money. The venture community here, many of my good friends, they have jumped on the bandwagon, and they are starting startups, and that's a good indication. That means nobody believes that these big four are really going to be able to solve all the problems. Otherwise, investors would not invest in new companies. And you saw 4 examples yesterday at Brillio at a smaller scale, right? So this is all encouraging, and things are going to happen, right? And this is the customary slide of many companies in this area. So I wanted to go back and go do some amount of soul searching, right? So what is this AI business, right? What is AI? And that's what James was asking me, and other folks were asking me, what's AI? It's really not very clear. So right now, right, it's a catch-all phrase for anything that does something with data, a complex software system, and increasingly a complex cyber-physical system where things move. You have sensors, you take that, you then predict, you then make the next move, and then the system responds, right? That's really what the rubric of artificial intelligence is, that almost everything, as Professor Sahini said yesterday, that anything you put data into it and digital becomes machine learning and AI, right? So not to be cynical about it, right? But that's the reality. So can we go deeper? So in my mind, there are really 4 broad categories that fall under AI. And they are very different in the scope of what they solve, the kind of tools they use, and the kind of use cases they have, right? So number 1 is what gets a lot of, do I have I must have. How do I turn on the laser here?
That's the red button.
The red button? Okay. Okay. Sometimes they don't show. But anyway, so first one is, can the machine behave like human? Right? So we have these personal assistants, we have bots who are supposed to behave like humans do. So it's really trying to understand humans. How do humans think? Can machines think that way? The second one, again, is the age-old stuff of robotics, that not only thinking, it will interact with the outside environment, right? So can it negotiate an unstructured or in an environment and do stuff in the physical world, right? And third thing is kind of very distinct from the other 2, and I think that's where a lot of your problems lie, right? And so feel free to stop me at any time, which is machine learning applied to organizations and operations. You have a ton of data about your factory, about your manufacturing process, about your business process. Can I predict stuff based on it? Can I build a model where then I can intervene and get a better ROI, make it more efficient, right? See, that has very little to do with the first one, which is understanding humans, right? In many ways. Maybe the algorithms are similar. Maybe the databases you are using, they're the same name. But the objectives are very different, right? And that didn't used to be, that used to be under business intelligence, right? Now under various rubric, because you had to solve this all the time. The moment you have a business, the moment you have an organization, all the problems are age-old problems, right? But they have new names. The progress, again, is very real there, right? And the fourth one is, I think, Puneet talks about a lot, right? Which I think is a totally left field stuff. This whole integration of virtual reality and augmented reality. So if you think about it, it has the potential to reprogram our brains. So anything we experience is how we program our brain. So brain has no keyboard, but it has portals. And the portals are the sensory things that then go and program the inherent models and the hardware of the brain. So augmented reality is a completely new way of, for our brains to experience stuff that it has not experienced so far in different contexts. So who knows? I put that in the X factor category, that what the outcome would be of that is just not known right now. There are indications, but it's not known. So where do I start? So let me start with, again, stop me. I can skip to any one of this based on your particular needs or curiosity. But in my linear presentation, let me start with, personal assistance. That's where, the first part, that is, the personal assistants have to simulate a human brain at a very granular level, at a very high level, at some level they have to, right? So what's happening there? Well, what's a personal assistant really? Let's break up the parts, because I think these parts get mixed up in our perception, and that's what leads to general confusion, both about the power of the machines as well as their limitations. You get either super excited, oh man, look, they must have something inside there. So we had, growing up, we had a cook in our village, in our household, and I was little. I was like 3, 4 years old, and I still remember. And the cook never believed that the radio. So how can this radio talk, right? So the model for the cook was this, that there must be little people inside, right? Now that's a very valid model. It's an improbable model, but that's what her way of modeling why the radio talks. Right? So I think in some aspects, I bring these corner cases out to make a point, that in some aspects, we have a very similar one, that this black box on the right, we tend to give it either more power than it has, or we try to strip it of all of its power and get disgusted and disappointed. But of course, reality, as always, is in the middle, right? So what's really happening? It's the schematics that you all know, but I think if we break it up in this way, it gives us some insights, which can clear up some confusions as well as open up new opportunities. So here is the human, right? Here is the human here. Oops. So there is the human on the left. The human gives us some output, like it talks, it shows us images, right? It types on a keyboard, and that's what gets to the machine. A machine's first job is to break up these signals. These are pixels. These are electric signals, right? These are sound waves. That's all the machine sees. Not like us, that it immediately, we don't even think. We get those inputs, physical inputs, electromagnetic waves, sound waves, and other stuff, and then we immediately process and parse it out. So first job of the machine is, for example, voice to text, right? Or from images which are pixels to objects, right? And then comes the harder part, and which is where all the devil is in the details of that, the human model. So, and then the new part is this cloud of big data, corpus, and repositories. That's what then the machine can look up, because the big data humans can't look up. But machines are very good at looking up big data, if properly structured, and for that you need partners like Brillio's, right? If properly structured, it's easy for machine to look up that big data. Then it gets some kind of an answer and feeds it back. And then we, in our great evolutionary heritage, we then assign humanhood or a personality to that machine. The machine has none of that. It's we who project that, right? So it's very important to remember. So where has progress happened? So this skin of it, good progress has happened. So like the speech recognition is good now. Alexa or Siri, they get the words that you are saying, right? Images, as I'll show, to some extent, it could get and progress has happened more than it had happened 10 years ago. And that's where the deep learning stuff comes in there. So the deep learning is really shallow in the sense that it's really getting you the skin. See, that's important to realize. And that's both, it's from a philosophical, from an intellectual perspective, it's its limitation. From a business perspective, that's where the power lies. So now deep learning. Okay, so any question you have about deep learning, shoot at me now or later. I'm going to give you some kind of a canned linear version of what deep learning is. That's not supposed to answer all your questions or educate you about it. So please, at this point, you need to be my friend, not like my undergraduate students who show up and then say nothing, and I have to tell them. Yes, please.
I just have one question.
Yes.
On AI before we move
Yep.
on. And that is, so my car, if I, with the navigation system, if I put the address, it pulls it up. Is that artificial intelligence?
Depends on who you talk to. Depends on who the salesman is. That's my point.
Seems like it might be to me. That makes basic sense because it's interpreting.
But right? So you were right. So going back to the system, so it's doing a version of this, right? You speak to it, and then it understands that layer, right? And then comes the structured part. It has been programmed to know the words in the context of navigation, right? And then the big advantage, which was not there, right, is that big database of geolocations, GPS, and all that infrastructure that it can access. So it falls in this category. So in that sense, it is, right? So that's why I don't want to poo-poo it by saying, oh, it's just looking up a big database. It's more than that. But at the same time, it's not doing anything that none of us in this room cannot do. Right? With that, any other questions? So this deep learning, I can go on and on about it. I wrote 2 books on it in the 1990s. Right? Now I'm back at it because it has been proven to be a success. Right? And so stop me at any time. I'll go at a fast pace. If you have some questions, please stop me. So.
What would you talk about as the best example? What is the deepest level of learning that any system that you know of exhibits today?
They're all domain specific. They're all domain specific. The more layers there are, right, where humans have invested, right? So it's really, most of it is very shallow.
It's Siri understanding what I'm saying and looking into the knowledge graph and trying to give me a specific answer that's perhaps as deep
as it gets. That's as deep as it gets, right? Now, for particular domains, it could be astounding, right? Like navigation. And it can anticipate, it can tell you, like Waze, combining Waze to Google. I'm always so impressed with Google Maps, right? It's a well-executed, a great product, right? So that's, to me, it's like, I always ask my students and myself that if you woke up Aristotle, what in the new world would he find really impressive? Yes, you had a question. While you think about it, let me take a, don't get me started. Yeah.
One of the things missing from the slides were about the IBM Watson product.
Yes.
I think of that as pretty advanced so far. Between the chess champion and
So again, IBM Watson is good execution. It's really layers and layers. It's disjoint units put in a natural language processing rubric. So the real thing is the natural language processing, the parsing, which is an old thing, right? Then what they do is bring in these kludges for each domain. They bring in their expertise on top of that. So if you go and ask Gary Kasparov, right, who lost to DeepMind, would he say DeepMind is, or what is the Deep Blue, whatever the thing, would he say Deep Blue is intelligent? He would say, he goes out of his way, said it's not absolutely intelligent. It does more searches than a human mind can do. So it's a raw power, which is good. Again, I'm not saying that, but see, when it comes to simple thing, right, that what is this image? Most of what I'm going to show you is most of deep learning just completely, absolutely, abysmally fails. But as a system, that's a great product to have, right? So I'm playing both the game, right? One is your needs, for which I think your needs can be met. They can be magnified. You can make great business decisions, absolutely. And that has not been exhausted. The other part of it is true philosophical, true understanding. And there is not much has happened. It's still very shallow.
So this conversation about singularity, we are very far from even having that, the beginning of that conversation, right?
Oh, yes. That's, excuse me, if I may be very direct, that's all, philosophical BS. We just don't have the model. See, you can say that something, like I can tell you that molecular electronics is never going to work. Okay, it's not going to get you down the Moore's law. Quantum computing in my lifetime is just not going to happen because physics just limits that. Okay, but to say something like singularity, you first need to have a model that models who we are as sentient beings. We just don't have that. It's just completely, throwing darts in the dark, So anyway, so the deep learning, it's a case study, a good case study in how we think, how our institutions work, educational, research, and our philosophy, just the intellectual institutions work along with the business. I think it's a very good study. So there's this people, McCulloch and Pitts, in 1945. One of them was at MIT, the other, I don't know. I might be wrong. It doesn't really matter where they were. So they said a very simplistic model that, hey, there's something we can abstract a neuron as a majority, weighted majority voter, which is that it takes many signals. It forms a linear weighted sum. If it crosses a threshold, it fires. If it doesn't cross a threshold, the output is 0. That's it. Now, it turns out that once you define that, it's a powerful model. So in the 60s, and there's Professor Bernie Widrow here. He's still alive. He's in his mid-80s. He's still thinking. He was a big leader, thought leader in this. He showed that if you take 2 or 3 of these, they can do some signal processing problems. And in fact, the algorithm he came up for noise cancellation is the one that still works here. All your cell phones have what's called an LMS, least mean square algorithm, which was a way of training one of these units. Okay? And after that, probably 10,000 papers have been written in how to do it faster, how to do it more rigorously theoretically. None of them gets implemented. What gets implemented is that simple, very heuristic thing that he did, which is based on how neurons learn, his abstraction. And that's what gets implemented even now today. And that's why you don't have drop calls, unless it's AT&T, of course, right? But sorry, the AT&T folks, it's just a joke. Don't hold me against me. Okay. So anyway, and then came Minsky, Marvin Minsky. He became a good friend of mine for 6 months. I got his full attention for 6 months in 1994 when he wrote a foreword to one of my books. Okay, but like all humans, we are all limited. So in the 70s, he just killed that field. He just said everything should be rule-based. We don't care about this connectionist approach of nonlinear units interacting, right? But then in 1980s, he passed away in 2011. He was a cognitive psychologist at UC San Diego, Dave Rumelhart, right? He really resurrected the multi-layer of these units, right? And call the method for training them as backpropagation. Now you hear Hinton is a guru at this. He was there at that time. He was not the person who really pushed it. He is a very good researcher, a lot of respect for him. He has stuck in this field since the 1980s, right? So he deserves all the credit. He was nowhere in the scene. He came in a few years later and picked up on that, right? But then what happened was, and that's when I jumped into that and I wanted to study it, right? And what happened was, in 2008, they had the right power and they had enough data. So they started applying the neural networks to images. And they got better results than other ways of doing it. So which I'm going to talk about. So that's kind of the resurrection. So I'm going to skip this, okay? This is kind of a self-promotion, right? That I worked in that field. I wrote 2 books. And here is Marvin Minsky here, forward by for this. And these are the two big gurus, Barney Widrow, who I said, and the person who really make backpropagation and stochastic gradient, which I'm sure you hear about in the press a lot. You know, they made them, they really implemented them, they came up with them, they give the algorithm, right?
Sorry, can I
Sorry.
just ask it? So if you go back to that timeline.
Yep.
So just in very simple terms, we said last night.
Yep.
very simple, what are the kind of applications that were being applied? Just to give some examples. Of
So I'm coming to that, right? Absolutely. So here is an application that this is where you see a lot of things, and I'll completely tell you that you know, the limitations as well as power. So the thing is, for the longest time, if you wanted to do image processing, computer vision, you will take this image over here, then you're going to apply a lot of filters, a manually defined filters to it to get features. So you take an image, you make it into a big, huge vector or whatever, you know, smaller dimensional stuff, and then you are going to design what are called classifiers around it. That is the state of the computer vision. So what features you get would be a huge study. Now, what happened was, this is when this person, Lacan, right, he came up with this architecture at the height of the you know, that 80s wave of neural networks, that I'm not going to do any of this feature engineering myself. Brain doesn't do that, right? The brain has these layers of neurons which are local, right? And it passes through them and features get extracted. So he came up with that, except we don't know what the F is going on inside the brain. Right? So he said, okay, I have the stochastic gradient method for training. So I'm going to take millions of images that are tagged, and I'm going to train them, right, and get an output. So this is a big application that you hear, and here is what goes on. So this is your deep net or image net-based vision. Okay? So someone, and this Professor Fei at Stanford University, she started gathering this database to train these neural networks. So there are 1.28 million, now there are 2 million training images, all cropped up, okay? Over 1,000 categories, they're expanding the number of categories. Then you put it in a machine that has few thousand cores in it, and you let that machine run for almost 3 weeks. And then at the end of it, you get an input-output relationship, right? That if you can put in a car there, right? And it goes through this network. At that time, it's no longer learning. It goes through the network, and it gives you whether it's a car or not, right? Now, there is some amount of science in it, in the sense that it turns out that, like the brain, this network, even though you didn't tell it anything, automatically learns like the different parts. This is layer 1 where it's getting the edges. This is in between layer. See, here is like it got the wheels, parts of the front. So it's as if it's breaking up the images into these different parts and then making a decision. But, yes?
So, looking at the car, and this is something Vwani and I were discussing,
Mm-hmm.
real problem. We're discussing, let's say, a shirt.
Mm-hmm.
I see a shirt, and using, image recognition, I want to recommend a similar shirt.
Yes. Yeah.
That one part is resolved, the color part, right?
Mhm.
When I'm saying a blue checked shirt, how do I know, right, whether the person is looking for a checked shirt, blue shirt, a certain material, certain style of collar? So when it
So-
basically brings in multiple dimensions, although it recognizes it as a shirt and every individual component, how does
It doesn't. Of course it doesn't. And that's the problem in this freaking field. Sorry. Okay. Don't quote me. I hope it remains within here. Nothing, no offense, anything. It's just the hype around it. See, this is what it is. Right? It has 1,000 categories. It has been trained by very well curated images, and that's all it does. It won't solve your problem. I have solved your problem, right? But that's part of my startup, which we put in $4 million. We developed the product. I want to be true to my academic. That's where I get my fun. I want to go on. The business people didn't deliver, so it's mothballed right now. But we looked at the problem, and to a large extent, we solved that. And we didn't use any of this deep learning BS. Okay, but it works. There was no system there. So here is what we'll do. You give it a car. It goes through the network. It outputs likelihoods of the 1,000 categories. Okay, so this one is saying, car is the most likely. Then there could be truck, airplane, ship, horse, right? Whatever. Okay, but that's not yeah. Go ahead, please. You had a question.
Just had a question for you. That's pretty clunky.
Yep.
Did you ever work with a Wang computer?
No.
Yeah. It was very basic, and you put certain things into it, and it fit kind of, it was big and heavy, and it was like the size of a tabletop. But it was state of the art in 1980.
Mm-hmm. So, and things worked, I'm sure, right?
It just brought out some calculations for us to use.
Yeah.
It took a long time.
Yeah. No, so all I want to say is that this one, that it would, with a high precision, which is again to be, so these are the precision, 60% precision, if you go by that, not more than that. Okay, that's the latest one. With 120 layers, 10,000 cores, working away for 3 weeks on this very scripted data set that has been manually trained, and it gives you this result. This is better than anything they had before. It doesn't solve your problem, as you pointed it out. Okay, but this is good. This is nothing wrong with that. It's good to be crowing about, especially if you're catering to your Wall Street, if you're Google and Facebook, right? You want to keep your people at Wall Street happy that you are doing rocket science. Even though rocket science is not really rocket science these days. Anybody can send a rocket out, but anyway, that's a whole different problem, right? But anyway, this is what it is. So, so coming back to our problem. Right? So this is the skin. So the skin has been done to some extent, especially in speech. The skin has been done, right? Especially in NLP, taking a sentence and then breaking up into syntax. That is good. That's good. It's a 30 years effort that has culminated in a good product. The problem then becomes, what do you do with these words? So, there comes Alexa, right? Or Siri or something, and they're putting in. So they get these words, then they try to make meaning out of it. And that's where the whole whole mess starts, right? In particular domains, it does okay because the domain is structured right here, right? I want to go eat, right? Now, if it is programmed that I want to go out and eat, right, then it knows, this person, I should look up these databases. So I have a profile, right, of this person tastes, where I am, that locality, right? I know all the restaurants nearby. I know how much money you want to spend, what you have spent. So you have built a profile, a model of this person with respect to some attributes. Right? And it can do a great recommendation, which I think is a great business idea. Same with which movie should I watch? Right? Again, if it has his history and it has access to Netflix recommendation engine, it does pretty well. I'm always impressed with the people Facebook suggests me to be friends with. One time, it was, I have no connection with this person. He was in my neighborhood, a neighbor across the street 15 years ago. His name came up. So I was like, how did it do it? Then I heard that Facebook got access to all this data. So someone wrote a filter that if you want to recommend people who have been in the same address, proximity, right, and do that. So this is great stuff. And this is something that, this is very impressive, Amy, the X.AI. Again, it's a scheduler, right? You can send it stuff. It builds your database. It has that quote-unquote understanding, which has been built in by someone, not by Google, not by deep learning, in whichever way you want to do. You can use deep learning to make the predictions, but you have to do the stuff, right? And this is where, in my mind, IBM Watson comes in. It has a very good natural language processing unit, right, which can break up the sentences and all in terms of the objects, subjects, relationships. And then it has these domain units that get plugged on it. But you still have to plug the domain units on it. And that's why they have few hundred data scientists, and they have thousands of people who go and talk to you. All right? Now, someone like Brillio, which has a great team, can do the same for you. Probably they will do better for you because it's not catering to 10,000 customers. But they have the know-how that's out there because of these advances. So, this is where some of my fun stuff happens here, right? What do we do? So to me, one of the problems you can say is understanding the humans better. And dogs understand us very well, right? And we understand dogs most of the time, right? They are a lot better lot better friends for us because they understand us. They understand our intent from our body language, from how we speak to them, right? So what do we do? And we didn't program them. They come with this unsupervised learning capability, right? So first part is this, right? That take another domain like this. The fact, state of health, being fever, and then running. See, the fact that running is an exertion, that how would the machine know that? No amount of natural language processing would give you that, right? See, it has to be built in. So here is the opportunity, right? So you can easily make now with the understanding of with the skin being done, and that being a commodity, you can now build on your own engine that understands humans and addresses your problems much more easily. And for that, you use the machine learning tools and all. But the brain itself has to be particularized, right? So here is, I'm repeating myself here, so I'll go over this again. Won't go over this. So to me, it's really unsupervised learning. And that's where the model is. Can I learn like a human does? What do I need to put into the machine so the machine can learn like the human does? So I asked this question to myself, that suppose if I put a portal here, so I call solving the aliens human problem. So if the aliens broke into the backbone of the internet, right, it will get a good picture of what humans do. The images, the sounds, the news, the articles, the logs, everything, right? It can easily find out that there are these videos which are furry animal is there, and people like them a lot, the cat videos. Right? It's not that difficult for aliens if they can do that. So how would they do it? So my problem to my student and myself was, so here is an example of why the deep learning thing is. So here is an image, right? I fed it to the state-of-the-art deep learning, not for learning. This is now detection. Look at what it got. It missed almost all the humans. It got some. It got some human, a helmet, person and a helmet. The rest of it is just, it missed the scene completely. And going to your point of Vijay, that's what its limitations, because it's not trained, even it was trained for human figures a lot. It missed almost all the human figures. And this is the state of the art output that's available out there, that this is an already learned deep neural network that has been trained, and that's what it's supposed to do. All right? So I asked my students that, and myself, sir?
Isn't there a certain amount of context to something like that too? Because going back to your alien example, if I'm looking at the Earth from outside, cars inhabit the planet, not people. So there has to be a certain amount of context to the scene. How does the machine know that?
So that's my point, right? Absolutely, absolutely. And that's my point, that what the hype you see is about what I told you, right? 1,000 categories, no context, cropped out images of the objects. That's what the machine has been trained on, right? I'm just highlighting the obvious here, right? Clearly, and this is where you can go and work. You take this machine vision tools, which are good. Then if you really want it to work in this setup, you have to build your own machine vision platform. Google is not going to do that for you. First, it doesn't have the manpower. Second, it doesn't move their stock market. Third, they're making money hand over fist, or whatever the way the expression goes, fist over hand, hand over fist, right? It has no motivation. Yes?
I think Kevin would make an excellent point, and I think that's exactly what you're recommending as well.
Exactly.
That we got to build domain-centric models. So we are thinking of, we're working on problems related to, hey, how can a conversational interface recommend or help a person identify what exact PC configuration that I want. So if you build in the context of the model and typical choices that you make, and then you apply the power of learning of the last
Absolutely.
million purchases that we have done, you can optimize the hell out of it. But you will have to be super specific and did I get you right?
Yep, exactly. And that, as I said, my talk is self-similar, and that's what I said in my first slide, and I'm just elaborating on that. So anytime you get bored, you just say, Vwani, stop it, we are done. So anyway, one of the things, before I stop, I have to bore you with what excites me, right? One of the things that excites me is, can I make this learning unsupervised? So how do we learn? We don't learn from random croppings of 10,000 categories of images. We learn contextually. So that's the problem that I have solved in this case scenario, that suppose if I give you lots of images where humans are a big presence. So some object is a big presence. I'm saying humans because I knew from before. But the machine does not need to know. There's no labeling whatsoever. Can I build a model of the object? What does the model of the object mean? That it should have parts, it should have different views of the parts, and it should say how the parts move around, how they are together. So I'm very proud of this work. So we got that there is something in this area, all of these are in this area of this object. And see, that arm could be in very different positions. But we discovered that in an automated way. We discovered this whole model in a completely automated way from 10,000 images without any labeling whatsoever. But the context is important. I can't learn in a random way. And this is not that difficult. In your businesses, you have context-specific images, context-specific content. Then you apply your learning algorithm on that.
I've seen the results. It's fantastic. I've seen some extraordinary amount of images. As you said, the fact that it is this arm in relationship with the shoulder, that irrespective of what position it is, the system is beautifully able to come up.
Yep. So this is, I give an example, a head detector. See, the face detector. See, there are whole programs available which detects faces. They will fail on this completely. We humans, are we going to fail on this? Even though we can't see eyes, we can barely see the nose. There is nothing there. Sorry, these are model images, nothing meant here, right? But from the rest of the body, we know where the head is. right? The whole deep learning supervised framework is just not meant for this. But this is how we do stuff. And real world is not going to give you stuff the way you teach your deep learning. Right? Yes?
So in this case, right, we could expect to know that's the hand, that's the
Yep.
body, that's
Yep.
the leg. Can we program it and say, hey, that must be a head on top of it?
That's exactly what I'm doing. In this, that's exactly what I'm doing. Because I don't have this kind of heads. Right? But I know the shape of the body. And that's exactly, you're very right. That's exactly what the model does. Because see, in the previous model, here, they're all related in this model geometrically. That if I know where the half body is, I know where the head should be. And that's how we are predicting the head there.
And then you have to anchor it, even, seems like on this picture, no, the learning picture, right?
Yep.
So you have to anchor the most stable
Parts that you
part of
detect.
the body, which
Yep.
is basically the trunk, right?
Yep.
Because that doesn't matter what pose.
Mhm.
It can only bend so much.
Yep.
Right? So once you have positioned that, then you have.
Or whichever part you recognize. Maybe the leg is there.
No, but
the leg, head.
actually can have more volatility in terms of how I place it. The trunk.
But you're right. Philosophically, you're right. Detailed wise, I can be more detailed than that, right? But you're totally right. So the same thing. So here is a fashion image. You pass it through there. It gets the human body, which is good. I was impressed with that it got the human body. Then it gets guitars and a cocktail shake, right? Maybe a mini skirt. It forgot that it goes all the way through the body, right? So again, I'm impressed with that it got something in here, frankly speaking, the deep learning. But within its limitations, but that's all it can do, going back. So in the startup 6 years ago, we went and we analyzed a body like this. We know the skin, we know the dress, we know the color, we know the style of the dress, because that's how we learned. So how did we learn? We did not have 1,000 people going around tagging, right? So what we did is we first learned skin, and we learned human body. The rest just followed. What's a dress? Is the part that you cover. And the shape of that will give you, so this was done almost in a completely automated way after that. What's a V-neck? V-neck, we learned, nobody told us what a V-neck is. We learned from the shape of all these images that are there once we took out the skin. So it's an unsupervised way of learning, right? So anyway, other types of AI. So here is a before, yeah, sorry.
So for that engine, right, accuracy, what's the accuracy rate?
We did everything 95% accuracy. So you are asking me, so we had to do a test, right? It was 95% accuracy across almost all the facets you can ask for.
So in measuring what? So can you identify
So
accuracy on the
gold
dress,
standard.
Or can you say that this is the same dress wearing by different people?
So very good question, right? It's a multifaceted problem. So what we do is we take that image and then we say all the facets. Then we get an accuracy on that. Then if you want exact match, that's a lot easier. See, that you don't need to know the different parts. See, what happens is what Avijit was asking, what's an approximate match? Right? See, exact match of images is a solved problem. It's just like looking up two documents, are they same or not? You take what are called hashes, okay? And then you see if the hashes match for these two. But the thing is, what do you mean by approximate match? So what we did was break up things into facets, like neck style, length style, hem style, color, pattern, right? And then you compare two images and see which facets match. Maybe all facets will not match. And there we also did, it's more like in the top 5, almost 95% accuracy in the top 5. what you were looking for. Now, what is accuracy is what humans would judge them, right? Because there is no, the gold standard is based on human judgment.
By making it unsupervised is particularly smart because if you make
Yep.
it supervised, you are catering to one or
Yep.
two outcomes, right?
Yeah.
So this can be posted.
So anyway, so you saw, I won't go through this, you can come on this. Arundo is a great example. So here is, before I go to my last slide, here is a good mind reading problem that I did with some people, okay? Don't think twice why you don't want to be human. Why doesn't the machine should not be a human all the time? It's a demonstration of that. Don't think twice. I'll ask a question, whatever comes to your mind is the right answer, so no need to impress me or anybody else, okay? Think of a number between 5 and 12. Okay, how many of you thought 7? How many? So this see, already I see like, so the statistics is 30%. 30%, so there are 8 options. If it was random, it will be for each one 12.5%, but 7 has like a 30% popularity compared to the rest. That's the human mind's bias. So unless you want to interact with humans, you don't want to be humans, the machine, right? So the machine learning and all does that, Arundo. And so here is a problem that I want to say before approach 1, approach 2, and that is again, so in one approach, you can take everything, all your data, feed it into a big machine learning like random forest and all, you can do that. In another approach, you kind of bring in the structure of the problem, and then you build a model of the data. So I prefer the second approach, and I think that's where you guys are. That's where you're going to have the best outcome. Yes?
So like if you think about pricing and assortment optimization, like
Yes.
things that are there for several years,
Mm-hmm.
would that be a kind of artificial intelligence under the approach too? Because you're taking a structured data set, you're putting some
Yes.
rules, like would that be
Yes.
artificial intelligence?
Yes. Yes. And there are machine learning which can help you do that, bring in the structure. So you don't have to specify all the structures, right? You provide some guidance, the machine learning can then crunch all this data and give you the rest of the structure. Then you can interact with it. That's an advance that has happened now. That's real, right? So parting thoughts, let's script all these nice figures.
Do you know of any company that is doing that with unstructured data for pricing and so on?
I don't know pricing assortment, no. But
A project on it,
there you go. Here maybe.
working on it in April, May, but
So parting thoughts. I could stop. I have said all this before. Great progress, great opportunities, big 4. They are not going to solve your problem. They're not interested in solving your problem. It's a great thing. Going forward, I wanted to, can you please, talking about a sentient being. Look what's happening. It's a puppy that's experiencing rain for the first time. Now that's a sentient machine there. It has a model that if it feels something, someone throws at it. So it's trying to figure out, where is this water coming from? Who is pulling this trick on me? Who should I fight with? Right? Because that's the model. It has a model, spatial awareness. Right? So you can stop it now, please. Thank you. It has the spatial awareness. It has an awareness and a model of cause and effect. Oops. Yeah. It has an awareness of cause and effect. Right? So it's looking for the cause for the effect it's experiencing. Right? And the third one is, even if we succeed, what will happen? See, this is something that you don't need to worry about it today. You will get to meet your quarter goals and all, right? But this is a bigger problem. Where are all the truck drivers going to go? It's going to be automated soon, self-driving trucks, right? So there's a precedence for it. Okay? So this is the knowledge graph of my company, which I'm very proud of. We did a great job. We have a better knowledge graph than Google, Facebook put together. But we're still struggling to make money. Okay? This is a concept called Luddite. It is automatically done. Nobody ever said anything to it. It's completely automatically created knowledge graph. And this is the neighborhood of Luddite. So Luddites were these people who were engaged in weaving clothes in England. So England not only put whole of India out of business, the cloth making business, it put its own people, cloth making and fabric making business people out of business. So the Luddites went around smashing all the equipment and all the companies. And you can see science and technology, industrial fear, industrial revolution, and some people wrote books about the Luddites recently, these two authors. But anyway, so, and the second issue, as I said, I started with the origin of the word data. It means to give. So you have access to it because someone is giving that to you. And then that brings in the whole privacy issue. Maybe for next 5 years, everybody is going to say, I'm not going to give the data. And then we're stuck because AI is no AI without data. Okay, so something that we need to worry about. And third thing is, which I think is the big X factor, which is the augmented and virtual reality. Maybe all you need to do, I keep saying this, that FDA, when a drug gets approved, you're lucky if the drug works for 30% of the population without side effects. That's about it. Now, it turns out placebos work 20+% of the time. But placebo is not replicable, so you can't have placebo as a drug. If there was a drug could be designed for placebo effect, then that would be the most successful drug ever. Maybe augmented reality is going to give you that placebo effect to program that. I don't know. The sky is the limit. Okay, thank you very much again.